Hello. Please hit like button and subscribe my channel. Also press bell icon for future video notifications. Thanks.
On April 15, 2020, a brief burst of high-energy light swept through the solar system, triggering instruments on several NASA and European spacecraft. Now, multiple international science teams conclude that the blast came from a supermagnetized stellar remnant known as a magnetar located in a neighboring galaxy. This has always been regarded as a possibility, and several GRBs observed since 2005 have provided tantalizing evidence, said Kevin Hurley, a senior space fellow with the Space Sciences Laboratory at the University of California, Berkeley, who joined several scientists to discuss the burst at Th. Those lasting less than about 2 seconds, called short GRBs, occur when a pair of orbiting neutron stars, both the crushed remnants of exploded stars, spiral into each other and merge. The most recent event, detected on December 27, 2004, produced measurable changes in Earth's upper atmosphere despite erupting from a magnetar located about 28,000 light-years away. Shortly before 4:42 a.m. EDT on April 15, 2020, a brief, powerful burst of X-rays and gamma rays swept past Mars, triggering the Russian high-energy neutron detector aboard NASA's Mars Odyssey spacecraft, which has been orbiting the red planet since 2001. About 6 minutes later, the burst triggered the Russian CONUS instrument aboard NASA's WIN satellite, which orbits a point between Earth and the Sun located about 930,000 miles 1.5 million kilometers away. After another 4-5 seconds, the radiation passed Earth, triggering instruments on NASA's Fermi Gamma Ray. The eruption occurred beyond the field of view of the Burst Alert Telescope (BAT) on NASA's Neil Gehrels Swift Observatory, so its onboard computer did not alert astronomers on the ground. Analysis of this data provided additional insight into the event. The pulse of radiation lasted just 140 milliseconds, as fast as the blink of an eye or a. Now funded by the Fermi Project, the IPN has operated since the late 1970s using different spacecraft located throughout the Solar System. Because the signal reached each detector at different times, any pair of them can help narrow down a burst's location in the sky. The greater the distances between spacecraft, the better the technique's precision. This is the most precise sky position yet determined for a magnetar located beyond the Large Magellanic Cloud, a satellite of our galaxy and host to a giant flare in 1979. Giant flares from magnetars in the Milky Way and its satellites evolve in a distinct way, with a rapid rise to peak brightness followed by a more gradual tail of fluctuating emission. These variations result from the magnetar's rotation, which repeatedly brings the flare location in and out of view from Earth, much like a lighthouse. Observing this fluctuating tail is conclusive evidence of a giant flare. Seen from millions of light-years away, though, this emission is too dim to detect with today's instruments. Because these signatures are missing, giant flares in our galactic neighborhood may be masquerading as much more distant and powerful. A detailed analysis of data from Fermi's Gamma Ray Burst Monitor (GBM) and Swift's BAT provides strong evidence that the April 15 event was unlike any burst associated with mergers, noted Oliver Roberts, an associate scientist at University's Space Research Association's Science and Technology Institute. In particular, this was the first giant flare known to occur since Fermi's 2008. The GBM also detected rapid variations in energy over the course of the flare that have never been observed before. One possibility is that the field high above the surface of the magnetar may become too twisted, suddenly releasing energy as it settles into a more stable configuration. Alternatively, a mechanical failure of the magnetar's crust, a starquake, may trigger the sudden reconfiguration. Roberts and his colleagues say the data show some evidence of seismic vibrations during the eruption. The researchers say this emission arose from a cloud of ejected electrons and positrons moving at about 99% the speed of light. The torpedo also factors into one of the event's biggest surprises. What's surprising is that all of these gamma rays appeared long after the flare had diminished in other instruments. The scientists conclude that this signal most likely comes from the magnetar flare. The gas piles up, becomes heated and compressed, and forms a type of shock wave called a bow shock. In the model proposed by the LAT team, the flare's initial pulse of gamma rays travels outward at the speed of light, followed by the cloud of ejected matter, which is moving nearly as fast. After several days, they both reach the bow shock. The gamma rays pass through. Seconds later, the cloud of particles, now expanded into a vast, thin shell, collides with accumulated gas at the bow shock. This interaction creates shock waves that accelerate particles, producing the highest energy gamma rays after the main burst. The April 15 flare proves that these events constitute their own class of GRBs. Eric Burns, an assistant professor of physics and astronomy at Louisiana State University in Baton Rouge, led a study investigating additional suspects using data from numerous missions. The findings will appear in the Astrophysical Journal Letters. Bursts near the galaxy M81 in 2005 and the Andromeda Galaxy M31 in 2007 had already been suggested to be giant flares, and the team additionally identified a flare in M83, also seen in 2007 but newly reported. Add to these the giant flare from 1979 and those observed in our Milky Way in fact, they may be the most common high-energy outbursts we've detected so far beyond our galaxy, about 5 times more frequent than supernovae. Video. www.youtube.com watch V = X66 BEB. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.